Yeah. So it's a joint work with Serdar, Erbatur, Andrew Marshall, Paliath, Narendran, and it's about protocol analysis and the application of, let's say, rewriting techniques to protocol analysis. And in particular, we are interested in what we call the Dolev-Yamo intruder model, where the idea is to represent messages by terms and to represent the capabilities of an intruder using equational theories. So we are really in a classical equational theory setting, and this is what we call the Dolev-Yamo intruder model. So a lot of systems have been developed based on this model, and here I give you a list. And let's say that all these systems are interested in determining what we call the knowledge problems. So basically, the problem is to determine what intruder can learn from the messages that are exchanged by a run of a protocol. And this is what we call intruder knowledge. So I will give you more precisely the definition of the problems we are interested in. So we have two kinds of problems. A first problem corresponding to a reachability problem, what is called a deduction problem. And we have also, let's say, an equivalence problem called static equivalence. So for deduction, the problem is to determine if given a sequence of messages and a term T that could be seen as a secret, can we deduce, let's say, the secret from the messages that have been exchanged during the run of the protocol. And so basically, the set of messages is represented by a substitution. We have a term corresponding to a secret, T, and we want to see and to determine if there is a context, S, for which we can get that the term S instantiated by the substitution leads to the secret. Okay? And so this is a kind of matching, except that a matching problem, except that in fact, here what is given is a substitution. And we want to determine a context. So in some sense, it's about context matching. And so this is what we call the deduction problem. And another problem corresponding to an equivalence problem is called static equivalence. In that case, again, we have substitutions representing sequences of messages, and we want to determine if we can distinguish one substitution from the other one. And in that case, we don't have to determine a term context, but we have to determine what we call a recipe equation, for which, for one substitution, the equality will be true, and for the other substitution, the equality will be false. And in that case, this would mean that the two substitutions can be distinguished. Okay? And so we would have, let's say, substitutions that are not statically equivalent. And what is very important to note is that, in fact, in the recipes, so term in the case of deduction or equations in the term of static equivalence, we are not allowed to use what we call private constants. So we have a restriction on the vocabulary we can use in the recipes. This is something very important to note. So of course, these problems are fun because they are undecidable in general. And so, of course, in that case, we need specific decision procedures for particular theories, and results are known already for a lot of particular theories. like blind signatures, encryption, decryption, malleable encryption. And many of these series can be indeed modeled via what we call subterm convergent term rewrite systems. So a subterm rewrite system is a very simple term rewrite system where the right-hand side is just a subterm of the left-hand side. So for rewriting people, it's very simple, very class of very simple term rewrite system, but it allows already to specify a lot of interesting properties with respect to, let's say, the knowledge of an intruder, especially for instance, encryption, decryption. And the good news is that the knowledge problems are decidable for subterm convergent term rewrite systems. And so there are decision procedures. And in fact, these decision procedures also work properly, meaning that they give, let's say, a right answer for theories that are beyond subterms. And here I give you an example of a theory which is beyond subterm in the sense that, okay, when you see, so this is a theory called blind signatures. So you have, let's say, rules that are clearly subterm. If you see the first 4 rules, they are clearly subterms due to the fact that the variable in the right-hand side occur necessarily on the left, because they are rewrite rules. But you have also this rule, which is not subterm, because in fact, sign of xz is not, strictly speaking, a subterm of the left-hand side. It's almost subterm, but it's not syntactically subterm. And so the idea was to understand what we really need to assume on the theory to get something, to get, let's say, decision procedure for theories that are slightly beyond subterms. And so for that, we have introduced, let's say, a rule schema corresponding to, let's say, a way to represent, let's say, how to compute right-hand sides that would be almost subterms. And so it's a rule schema that consists of 4 rules. So it looks like an homeomorphic embedding, but we have more rules. We have, let's say, the first rule corresponding to get a subterm. So this is a very simple rule, but we have also, let's say, a second rule corresponding to removing an argument. And so this means that here we are in a setting where we can have variadic operation. So this is why we call it a rule schema, because it's not really a classical term rewrite system in the sense that we are considering variadic operators. And we have also we have 2 last rules that are very important. And the first of the 2 rules is the rule 3 that consists of removing the operator G. And so here you see that we will increase the number of arguments in the right-hand side. Yeah, so we will not maintain the same number of arguments. And we have the same behavior for the rule 4. For the rule 4, we remove the function symbol G, and for the rule 3, we remove the function symbol F. Yeah, that's it. And again, we do not preserve the number of arguments on the right-hand side. And here it's a formal definition of what we call the graph-embedded term rewrite system. So it's a term rewrite system where the right-hand side is obtained by this rule schema, by applying this rule schema. And in addition, we also consider a kind of permutation to complement what we do already during the application of the rule schema. And so this is what we call a graph-embedded term-rewrite system. And here I show you how blind signature can be seen as an example of a graph-embedded term-rewrite system. First, we apply the rule 1 to get the subterm. So by applying rule 1, we get, strictly speaking, a subterm. Then we remove the blind by rule 4, and then we get a well-formed term using the rule 2 by removing one of the 3 arguments. So it's really an application of the graph, rule schema I've shown you. So what we know about this class of graph-embedded term-rewrite systems? First of all, it's too general in the sense that there exists a graph-embedded convergent term-rewrite system for which deduction is undecidable. So this means that we had to restrict how to apply the rule schema to get something for which we will have decidability. And this is why we have introduced a subclass called contracting, which is obtained, let's say, by having a rule strategy in order to apply the rules of the rule schema. And the good news is that for the subclass of contracting term-rewrite systems, it's possible to get decision. We have decision procedures for both deduction and static equivalence. So this is a good news in the sense that it generalizes what we knew already for the subterm convergent term-rewrite systems. And in fact, to prove that, we can rely on a property which is called local stability, which was already designed to show decidability of deduction and static equivalence in subterm convergent term-rewrite systems. And to be a bit more precise, a contracting term-rewrite system is a term-rewrite system which is obtained, let's say, by applying the rule schema following a given strategy, and where, in fact, we also consider additional projecting rules. So what is a projecting rule? It's a rule of the form, you have a term left-hand side containing a variable leading to a variable as the right-hand side. So it's a very simple case of subterm rule where the right-hand side is just a variable. And so it's a particular kind of rules called projecting rules. And to define properly a contracting term-rewrite system, we need this kind of additional projecting rules to get the right property called contracting. Okay. And so in the paper, in fact, we are studying what happens beyond contracting. We knew already a result, a general result about homeomorphic embedding. And we have shown also in the paper that, in fact, I missed something in the previous slide. In fact, to define a contracting term-rewrite system, we need projecting rules, but we need also a strong assumption on right-hand side. The right-hand sides must be very small. Not just variable, we allow depth 1, depth 2, but no more complicated terms. We have a strong depth restriction on the right-hand side. And so we have tried to show that, in fact, when we try to avoid this restriction, we get into trouble, in the sense that we get easily undecidability. And so this is what we have shown in the paper. And to do so, and to prove the theorem stated in the slide, we have in fact, use an encoding based on linear bounded automata. And so we had already a proof to show undecidability of static equivalence in permutative series, and we have adapted that proof to get undecidability of, for this case, where we try to where we consider term-right system without the depth restriction. And we have shown also two complementary results. The first result is about trying to see what happens when we apply just rule 4, graph-embedded term-right system. And again, we get undecidability, but for that case, we use an encoding based on a modified post-corresponding problem. And we have a similar result when we consider just rule 3 graph-embedded term-right system. So it's very easy to get undecidability, but hopefully we have also good news in the sense that we have also combination results. And especially we are able to get decision procedures for combined theories where one component of the combination is a term-right system, the second component is let's say a permutative theory closed by paramodulation. And if we have that the term-right system is E-convergent and also contracting, then we get decision procedures similar to the ones that have been already shown for the case of subtone convergent term-right systems. So we have also good news in the paper. And the related procedures are based on reduction techniques. And here I give you the reduction for the deduction. And so the idea is to of the reduction is to go from, let's say, the combined theory, I mean, deduction in the combined theory to deduction in the theory E. And this reduction is performed using a saturation process that leads to a new substitution, which is called here, which is denoted here, phi star. And this completion of the substitution phi is obtained by adding new deduced terms in the substitution. So the idea is really to enrich the substitution by new deduced terms. And this allows us to get the reduction. So this is the first, for the first reduction related to deduction. And for static equivalence, again, we have a reduction, but the reduction is a bit more complicated in the sense that, again, we need to massage the substitution. And especially here, we use substitutions, and we consider substitution denoted by the bar, so phi bar and psi bar. And these substitutions are again obtained by a saturation process, and in addition to the saturation process leading to deduced terms, we have to replace the deduced term by the recipes. So we omit the substitution and we have just the recipes, and this is how we get these new substitutions. And so these new substitutions allow us to get the reduction. And in particular, for this static equivalence problem, we also need to check some recipe equalities candidates. And so this is why we have a conjunction of 3 conditions to check. But let's say that the idea was just to give you let's say, a flavor of the kind of reduction we need for static equivalence. So it's much more complicated than for the deduction problem. And so now it's time to conclude. So to sum up, in the paper we show some undecidability results. And especially we have shown that it's very difficult when we try to go slightly beyond contracting. We get easily undecidability. So we have to be very careful if we want to try to weaken a bit the contracting definition. But on the other hand, we have also obtained new decidability results in particular for combination of contracting camera-right systems plus simple permutative series. By simple permutative series, I mean permutative series like commutativity or shallow permutative series. So very simple series. And actually, we are not yet able to consider more complicated permutative series like associativity and commutativity. So this is really the next theory we would like to focus on. What happens when we consider associativity and commutativity regarding deduction and static equivalence. And this, of course, of interest for theories like the exclusive OR theories, which, of course, is based on AC encoding. Okay, that's it. Thank you.